So people who need account forms, we have everybody here. Okay. Good. So something got screwed up with, I don't have the first slide for the third lecture yet. I'll have to get that in the break. So I'll just announce, I see that people are forming teams. That's nice. I'd like to have that done. It'd be nice to have that done this week or something like that, or early next week, before we start thinking about handing out projects. So anyway, just to keep that in mind. Feel free to use the notice board. Last time I tried to suggest that people who need partners and gather over here, but you can also use the notice board. I don't know how successful that's been. People should be, I hope you're all reading that from time to time, because announcements and other useful information will get posted there. Let's see. And I will be handing out, we'll talk about homework when it comes time to hand it out next time. I do owe you, yes, I know, I do owe you a schedule of when all the tests and so forth are, so I'll try to get that out by the next lecture, so that you can plan appropriately. All right, other administrative questions or other issues? So again, those of you who still need an account form, we have the TAs up here in the front who has them. Okay. So where we were last time, we were talking about this first phase of the compiler, where basically the problem, in other words, that we're dealing with is eventually converting text into an executable program, or actually executing it. And we're starting with a first step, which is breaking the text down into constituent pieces that correspond to the way that we naturally think about describing the language. So we have this example of SL1. It has these lexemes, and we had started looking at a program that would allegedly do these things. So let's see, what is this? This is not what I want. This is in fact something entirely different. All right, where are we here? I can remember which one I pushed to get the thing that I need. Let's see, nope, not that, and not that. All right, we seem to be completely out of these things. Here. Huh. Okay, what machine are we on here? Oh, we're on the wrong machine also. Oh, here we are. All right, so we looked at this Java program, which essentially just uses pattern matching in Java to extract the next token, and it just uses Java regular expressions. And I had this little piece of code that you should examine at your leisure. It's online as well. That goes through and looks at, this is not necessarily the best way of doing it, but it's one of the things that Java gives you. Now, if we look at what other things we have here, here's a Python version that essentially, it's basically a transliteration of the Java version. We have, and here it's another thing you can look at. So here I've just defined a bunch of, for the syntactic categories, I'm using strings in this particular case. That's another choice, since Java doesn't actually have an enumerated type. And I have a program basically that takes this funny little map down here is just a trick whose purpose is to take any particular string. Python strings are like Java strings in that there are multiple ways of creating, say, a string like numeral. You could create it either by using a literal like that, or you could create it by concatenating n and u and m, and you tend to get different objects when you do that. So the only purpose of this map here, the token map thing, is to provide a way. Oh, I didn't notice that these lights were on. Let's see, what's the thing for turning the front ones off? Do any of these things work? No, these things do not seem to be applicable. Well, I'll have to go back and find out where all the lights are in a bit. So the idea here is that I will take any string and I will map it to one particular instance of that string, so that from then on it's very easy to compare strings. I just use pointer equivalence, which in Python is written as is, and then I have and then what I do. So my token file basically looks for all of the tokens that match this particular here. Again, it's trying to color. It's trying to be helpful, but it's failing. Okay. So again, I just look at all the tokens that match one of these things, and this is basically, as I say, a Python transliteration of the Java code. Now, the final thing, however, is to use a specialized tool whose purpose is that's basically intended to find tokens. And again, we have to try to make this thing look nice. Now, this particular tool is called Flex. We'll be using a somewhat different principle in the project, or at least we can use a different principle in the project. And this is specifically intended for this task of finding lexemes. So in this little tool, this little language, we simply put down the tokens that we want. So there on the left side, you see that I accept any white space token up there at the top. Comments are the second rule, and then each of the tokens that I want to recognize gets its own line, and I just put what I want to do with that token, how I want to identify it. I put that over here in this action, and that's basically it. So all of that other machinery that was in the preceding file for reading the file, going through it one thing at a time, that's all taken care of inside the program that gets generated from this file. So this is an example, this is sort of our first example of a specialized tool, specialized to do one particular piece of a general problem, which is dealing with text-based interfaces, converting them into pieces that are convenient for the rest of it. And it's this sort of tool whenever you have it available, and when you don't have really intense demands on performance, this is a good sort of thing to use these tools. All right, so we will be doing more on that later, but this is just a flavor of the whole thing. And then, and now that we've done that, let's take a look at. Let's go back to the lecture part here and consider a couple of problems, and consider some problems that we might do. So we'll do just a few of these because I've sort of overrun the last lecture. But based on what you've seen, let's consider describing a couple of these items. I don't think I have. Oh, I do have them. Okay, so let's look at decimal numerals in C, for example. Now, we have a slight problem here because people who are getting this on screencast won't necessarily see this. So I think what I'm going to do, I'm going to try. I don't know how well this is going to work for them. In fact, I don't even know if the screencasting on this class is working. I haven't checked it out. Has anybody checked it out? Yeah. It is working. Okay, good. So let me just switch back to something that I can modify, like, for example, Emacs in here. I've got altogether too many windows on this screen. It's not good. This one we can get rid of. And we can go back and look at him. All right, so the problem here is that I would like to, so what I'm going to want to do, whoops, pardon me here, let's see, is, okay. So what I'd like to develop here is a pattern that matches numerals in C. That is to say, integer numerals. Let's say signed integer numerals. So this is an easy one. It's a sort of a warm-up. So what do? Numerals in C. There is one little gotcha, but we'll see. Do we have any takers? Yes. There's the optional negation. Okay, so an optional negation. So how would I write that? Minus question mark. Okay, let's see. Okay, fine. So we'll do minus question mark. So any comments so far? Pardon me? Yeah, it could be plus also. So what do I do? Okay. So a little technical point here, if you're going to, the character class, since character class uses minus as part of its syntax, you have to be careful that if you want to do that, you put it first. If you want to include it in the characters class, you put it first. Okay, minus, plus, question mark, fine, now what? Yes?
Some number of decimal numerals.
Okay, how would I write that?
Not very familiar with regexes.
It's any way that works is fine. Yeah. Okay. All right, so here we go, 0 to 9. Geez, I really got to be able to, yeah, I've got to get my glasses. 0 to 9 plus, okay. Minus plus question mark, 0 to 9 plus. Okay, any comments on that? Yeah, we're not going to, let's just worry about matching the string and we'll worry about how to handle the fact that there might be other stuff after it some other time. Okay, we'll just matching this numeral. Yes? Oh, no, I'm perfectly happy with using the, with commas. No, these are C numerals. No, there's a, well, maybe we'll do another example. Okay, but that's in a moment. Okay, so, yeah, now, this isn't actually, I'm going to tell you, does somebody have a comment?
Do we care what base it's in?
Decimal numerals in C. Yes? You don't want to say anything more? Okay. Yes? Yeah, there you go. That's correct. Yes, the number is not supposed to start with 0 or it becomes an octal number. And I said decimal numerals in C. So this is not a decimal numeral unless it's, well, I mean, I guess there is some, I don't remember whether C classifies 0, just plain 0, as a decimal numeral or not. But it might as well be an octal numeral. Okay, so to be a decimal numeral, we have to start with something other than 0. So how should I modify this? Well, you objected. Can you fix it? Okay, so well, the first character is allowed to be 0. The second and subsequent characters are allowed to be 0, right?
Yes. So before the 0 to 9 bracket,
Uh-huh.
not 0.
Okay, well, we could do that. So you're suggesting we have something that looks like this? That's not going to quite work. You're almost there. Yeah. 1 to 9, okay. And, all right. Okay, we're going to take all the credit. Fine, that's good. All right, there we go. So it's not necessarily trivial. There are always these little gotchas. But there you go. Okay, so that's C numerals. So that's C numerals. Oops, numeral double, what? I don't know. Okay, now there's another programming language that you've probably not heard of. It's called Ada. Now this one, named after the daughter of Lord Byron, interestingly enough. Ada was Ada Augusta, the Countess Lovelace, the first modern programmer, back in 20s or something like that. She was Babbage's assistant. And this programming language was commissioned by the Department of Defense, and it was invented, oddly enough, by a Frenchman. I don't think in today's political climate that could ever happen, but it did back there in the 80s. So in this language, decimal numerals, plain decimal numerals, they're actually numerals are kind of interesting in this language. In plain decimal numerals, there's no restriction about 0 at the beginning, because that's not how they specify octal. But this particular language allows underscores in the middle of the numerals in order to, in place of commas, because commas already have a meaning in programming languages, so they couldn't use commas. So they used underscores. However, the inventor was kind of anal about this, and he decided that in order to be a valid numeral, you could not have an underscore at the beginning or end, and you could not have more than one underscore in a row. All right, got that? So these are decimal numerals. They have digits in them, and they have, I was afraid of that. They have digits in them, and they also have underscores, but the underscore cannot occur at the beginning or end, and you can't have more than one in a row. So how would I specify that? Okay, we have a couple. Let's see. I don't think I've called on you. Yes, what do you think? Oh, no, you can't edit it. As new line characters in white space are never part of a numeral. So we're just going to recognize the numeral. In the back.
Bracket 0 through 9, underscore question mark, bracket 0 through 9. Sorry, bracket 0 through 9 plus underscore question mark, bracket 0 through 9.
Okay. And that's an underscore question mark, excuse me. Okay, now you can have any number of underscores throughout it's like, 1 million could be written as 1 underscore 000 underscore 000. Yeah, and sorry, you can have more than one. So we need a little bit more augmentation. Let's see, yes. All right, now you don't, again, we can start from 0. We don't have to start with 1. So 0 through 9, underscore question mark.
And in parentheses, 0 to 9, in brackets.
Does the bracket end here, by the way? Does the first, oh, that's a square bracket, I'm sorry. Okay.
Yeah.
Okay.
And then after the question mark, parentheses open.
Okay.
And in brackets, 0 through 9, plus.
Was there a plus back here, by the way? I think. Okay.
And then underscore question mark.
Okay.
And then in brackets, 0 through 9, plus.
Okay. So let's look at this. Does this look like it's going to work?
Except it's not going to work for numbers that are only 2 digits. Or you have to get at least 2 digits. That's the problem.
Hack everything before the open paren.
Pardon me?
Hack everything before the open paren.
Drop everything before the first open paren?
No, that won't work because that will allow an underscore. No, you're right. That'll work.
That's right. We don't want an underscore at the beginning. Good, okay. So we'll just get rid of this guy. 0 through 9 underscore, optional underscore, star, and then ends in, it must end in at least 1, 0 through 9. Okay? And let's not worry about the sign, if any. I think actually, to be honest, in most of these languages, the sign in front is not considered part of the numeral because that would make it ambiguous with unary minus, as in, is it the unary minus operator applied to the positive numeral 1, or is it the negative numeral minus 1, and it always leads to confusion. Okay? Let me see. Well, wait. Let me first of all make sure I believe this works. Yeah. Okay. Right. I think that should probably work. And of course, it's a redundant. There is some ambiguity in exactly how it matches the numeral, but that doesn't actually matter. So, for example, we can either, if I given the numeral 1, 2, 3 underscore 4. It can match it either as 1, 2, 3 matching 0 through 9 and then underscore matching the underscore question mark, or it can match it as 0 underscore question mark, but the option is not taken, 1, but the option is not taken, and so forth. So you have various ways of matching it, but it matches it nevertheless. Okay, well, I think these are a few examples. You seem to be getting it, and you can work out. The things get more complicated when we get to floating point numerals. Those become particularly interesting. But the rest of these, I guess I can give on homework or something like that. Actually, to be honest, there are some other answers in there are actually some other answers in the lecture. If I can ever find it again. Let's see. So that's lecture 2. I said lecture 2. What is the matter with you here? Okay, there we go. So I had a few solutions of my own. They get rather complicated. Okay. So that's all very interesting, and we can do further examples of this. Now, there is occasionally you'll have some fancy problems. For example, in Python, there is this funny rule that says that a block of code, a bracketed block, starts with an indented line, one that's indented more than the line before, and that block runs until the indentation returns to what it was before the first indented line. And this allows for inner bracketing because you just indent more and so forth. Well, there's not The only way you're going to handle that, as you'll see when you actually go and handle it, is that you have to sort of keep track in a separate data structure of how much indentation there is. You have to recognize initial indentation, and you have to do some fancy little use some fancy little features that are in your tool because people encountered this problem before. So that all works. Okay, so I think that'll do it. That does it for the introductory examples of all this stuff. And now we're going to, we'll now turn to an alternative way of doing the same thing, and we'll also turn to the whole question of how you implement this, how you get fast recognition of these things. Not that speed is always of the essence, but sometimes it is, so it's sort of nice to know how to do it quickly as well as how to do it, period. But if there are there any other questions? Let's take a break at this point, because I have to pull up a new version of this lecture. Okay.
Comments in C++ and Java. For the second example, why does the dot character inside the root not match star and forward slash? What guarantees that we end the comment with the last two characters?
Oh, yeah, this has to do with matching. I don't say this, but in the context of this thing, you imagine that you're using this pattern to match an initial portion of the rest of the input. All right? So what does that match? Well, by making this a lazy match here, it says that it will match only up to it'll match as little as possible
before you get
to the first star slash.
Thank you.
But that's only in that context. It's kind of confusing. I admit it's a little bit confusing because in the other ones I'm just sort of assuming that we're matching an entire string, but here we're doing a slightly different task.
I just missed a lazy one.
Yeah. Well, yeah, but if the task were to match an entire string, then this wouldn't be right, because in that case, lazy quantifier or not, the lazy quantifier wouldn't change anything. You wouldn't match the entire. It would successfully and incorrectly match a comment that had two star slashes in it. So you've got to be rather careful. So I should append a note explaining that this only works under certain assumptions that are different from the other. Can't be right. This is really annoying. right, and finally, let's see, do we are getting any luck here? All right, well, I'm mystified. So we'll just have to skip this for the moment. Ah, dear. Print? Honestly. All right, you. I'm getting a little bit peeved here. Good. Okay. Let us continue with an old version of Lecture 3 in that case. So ignore this first line. I had some more material that I prepared, but for some reason it's very reluctant to give it to me. All right, so what we're going to look at now is implementation. Now, to a certain extent, no, I don't know that this is extremely important that we do implementation, except because you can just use tools and not understand them. But on the other hand, there are some concepts that we touch on in doing this that are useful, that you'll find useful elsewhere. So there is a classical way of dealing with these basic regular expressions. It does not work, by the way, for general Perl-style regular expressions. Some of those features that I mentioned, such as nonlinear patterns, as well as capturing groups, requires additional machinery that essentially turns the problem from being a linear algorithm, meaning the length of the string that you're matching, into an exponential problem. Result, the lectures that you get out of Java and Perl and so forth, unless the implementation goes to quite some effort, can be kind of slow. But there's a fast implementation that's linear and linear time. And it's sort of traditional that we take you through it. So I'm going to take you through it. But the real reason for doing this is that there's this interesting concept that we get into by doing this, which is that of a finite automaton. And now you've probably seen these things before in some context, or you may have seen them in some context, or ubiquitous in computer science. So a finite automaton is simply a graph in the sense of CS61B. Its nodes represent what are called states. You can think of them as states, as in states of one's memory, of the machine's memory. And they're called finite automata because there are a finite number of these states. So if you think of this, if you think of the things as programs or as computers executing programs, which is one way to think of them, they are programs that are very limited. They're programs where you can think of there might be just one or one integer variable with a limited range, or perhaps a bunch of Boolean variable, a finite number of Boolean variables. We have some initial state, some starting state, and we have some bunch of the states that we just designate as final states. And the idea is that we are going to, so this is an example of an automaton. Each one of these, the idea is going to be that we start the automaton in the start state, which is the one that at its base. And we then read a piece of input. We read some input. And each time, as we go through the input character by character, we follow the arrow that has that character, that is labeled by that character. So here, for example, this is for recognizing strings of zeros and ones. Every time we see, if we're in this state and we see a zero, then we repeat this, and we just keep doing this until we've exhausted all the characters in the string. Now, one of two things can happen. One of three things can happen. First thing is we can come to a character, we can be in a state, and we can have a character that doesn't match either, doesn't match any of the outgoing edges. In other words, there's no character. If I had a string of zeros and ones and all of a sudden I encounter a 5, then this machine would say, ooh, a 5, I don't know what to do with that, and it blows up, right? So it falls apart, we'll say. In some formulations, there's an extra state called the error state, and everything that doesn't work just goes to that state. All of the characters that are not mentioned in the string in these transitions get piled onto a transition. That you get through all the characters in the string, you get through the characters in the string, and you end up in one of these plain, ordinary blank states like this that has a single circle, a non-final state. The final states here are denoted with double circles. If you end up in a non-final state, then you are said, or if the machine falls apart, then meaning that for any given character, there is exactly one transition out of the state, or out of a given state for that character. 1 or 0 transitions out of the state for that character, so that it's unambiguous what the next state is. We can also have these also come in a non-deterministic variety. In that case, it is legal to have more than one state for the same character. And the rule there is that if there is any way, if at the end of the string, there is any way that you could have, or any choice that you could have made to get to a final state, then the string is accepted. And if all possible paths that follow the input end up either blow up or end up deterministic and non-deterministic finite automata. And then finally, we have in non-deterministic automata, we also allow transition to a new state that just happens spontaneously in the absence of any input. That's called an epsilon edge. And in that case, you just go to a new state, and that's it. Now, it might occur to you that if that, with a bunch of, you could get a circular loop and go into an infinite loop, and I said that this was supposed to be linear. Well, as we'll see, that doesn't actually matter, but that's another matter for a little bit later. Okay, so this is what exactly does this DFA recognize? So in other words, what strings, if I start over here, what can you tell me about the strings that will get me to one of these 4 final states? Think about it for a bit here. Okay, that's almost correct. So he's saying that the number of ones in the string is either 1, how much? 1, 0, okay. 0, 2, 3, or 4, mod 6, modulo 6. If that's the number of ones, then it accepts it, and otherwise not. Or in other words, another way of saying that is that it's either 0 modulo 2 or 0 modulo 3, or both. Either one will work. That's right. Okay. So how would I write a non-deterministic finite automaton that recognizes that? A nice simple one. Yeah. Pardon me? The same one. Yes, very good. Okay. You see, now this is a man who understands strategy. Okay. There is, to any question, there's going to be a trivial answer or a trivial part of the answer, and you can give that, and it makes you look smart, and that's good. Good. You get a point for that. That's very good. But I think maybe it took us a while to puzzle this out, and I think maybe that you can come up with another NFA that is clear, that is easier to understand. But that's correct. A deterministic finite automaton is also a non-deterministic finite automaton. It's a trivial sort of non-deterministic finite automaton. Any other takers? Okay, well, I haven't called on you for a while, so go ahead.
I think you have, maybe the first two states are
Uh-huh.
but for the second one, you notice, the transition for the second state,
Uh-huh.
one arc goes back to the beginning. So that looks for...
Okay, I think I understand what you're saying. So we'll have one of these where from here we go back to the beginning, and then another one where goes to a third one and then back to the beginning, right? Okay. So and then all the rest of them can go away. Any comments on that? So I guess the only final state in that case would be what? The first one. Okay, so we make only the first one a final state. And then we have a transition that goes from the I keep pointing at this. We have a transition that goes from the second state back to the first, and we have a transition that goes from the third state back to the first. Okay, any comments on that? You're getting the idea, at least. So that's a 3-state automaton. Thoughts? Yeah? It doesn't matter which for the moment, it doesn't matter which final state you end up in. So is this one going to work? We change this to a 3-state machine with arrows back, with the first state being the final state, and arrows back from the second 2 states back to the first. Yeah?
No, it won't work. Because, for example, if they were 5 bits, go through the first 2 at the final and 3.
Right. So in other words, we only want to go, if it's going to be modulo 2, we only want to go modulo. We only want to test for modulo 2. We don't want to mix them up. In other words, we don't want to see if this is equal to 2 plus 3. We only want to see if it's equal to 2 plus 2 or 2 plus 2 plus 2 or 3 plus 3 or 3 or so forth. So any other suggestions? Another suggestion? Yeah.
We have from the beginning to epsilon transition. And both the states that it goes to will be like double circles. And then, so one on the top, it'll be like, it'll check the even ones, and the one on the bottom will check multiples of 3. So the first one will be circled, go to another one with a 1, then it goes back.
Yeah, okay. Oh dear, I see. I should have added the answer to that. Okay, so the answer is make 2 machines, basically. one of which recognizes modulo 2, one of which recognizes modulo 3, and and then you go to each one, take advantage of the non-determinism, and go to either one non-deterministically. I apologize to the people watching this on screencast. I will augment the lecture notes with a solution to this. But basically the idea is something like this. We have a starting state. That's here. We have one state which is one state that looks like this, and we have another state that looks like this. These are the ones, and there is the usual zero transitions. I won't put those in. And that's it. So yes, that's how we use a non-deterministic machine. It has the same number of states, but I think it's a somewhat clearer machine in the sense that you can tell that this is explicitly modulo 2 or modulo 3. And as we get, if we had something that was more complicated that had maybe modulo 3, 4, and 5 and so forth, it would get more interesting. Okay, we'll have to stop there and take it up next time.